Hello and good afternoon, friends. Welcome to the CEC-UGC live lecture. Dear friends, as you know that we have started with a series that is on reaction mechanisms, and under this series we have conducted numerous lectures. With the help of these lectures, we believe that we have helped you out in studying your course material. Dear friends, in this lecture today we are going to discuss on nucleophilic substitution reactions, and for this we have again with us in our studios Dr. Aprajita Chauhan. Dr. Chauhan is Associate Professor in Department of Chemistry, Sri Aurobindo College, University of Delhi. So dear friends, let's take advantages from her experiences because I would like to quote that Dr. Aprajita Chauhan is constantly engaged in numerous works regarding her work, as well as nowadays she is authoring books on chemistry. We hope that soon we would be getting those books in market. So without wasting time, let's first of all once again introduce our guest, Dr. Aprajita Chauhan. Dr. Chauhan, welcome to the EDISET lecture.
Thank you, Geetika. Thank you for such encouraging work and words, and for telling students that maybe I'll be able to help them further with my book, which I hope will be a lot of resource material for them. Now we will go back to a lecture. In the last lecture, we were talking about nucleophilic substitution reactions. In this lecture, we will have a closer look at nucleophilic substitution reactions. In my previous lecture, I had discussed with you mechanism of nucleophilic substitution reactions, that is SN1 reaction and SN2 reaction, in great detail. So first, what we'll do in today's lecture is we will have a brief review on SN1 and SN2 mechanisms, and then we will go on to, for example, if a substrate is given to you, how will you decide whether that substrate will undergo SN1 reaction or SN2 reaction? Is the substrate only important for the reaction, or are there other factors also, like the strength of the nucleophile, the solvent effect, the leaving effect, and other electronic effects also? First, we'll be discussing this. Then we will go on to discussing nucleophiles in detail, that is the ambident nucleophiles. And maybe if we are left with some time, then we will discuss that nucleophilic substitution reactions are also taking place in biological systems, that is plants and animals. And we will discuss the transfer of methyl group from methionine to choline, which is a very important neurotransmitter in animals. So now, to start with this, let's have a brief review at what we did in our last lecture. In my last lecture, I told you that if we talk of an SN1 reaction, SN, nucleophilic substitution, 1 is unimolecular. That is, the rate of the reaction depends only on the concentration of the substrate. So, in this case, we will look into the carbocation intermediate which will be formed in the reaction and the factors which will stabilize this. Secondly, since carbocation is formed in this intermediate as an intermediate, and if we start with a optically active compound, then this reaction is accompanied by racemization. Whereas if we look into SN2, which is a bimolecular reaction, in this case both the nucleophile and the substrate are taking part in the reaction. So the factors which will stabilize the transition state will increase the rate of the reaction. Second, since the bond formation and bond cleavage is taking place in these reactions, therefore this reaction is accompanied by inversion in configuration. These are the details of the reaction mechanisms. Then if we look into the factors which are playing an important role, then they are the structure of the nucleophile, which is the most important. So now the question arises, which mechanism, SN1 or an SN2 mechanism? The most important factor which helps us is the structure of the substrate. That is, if the substrate is methyl or a primary alkyl, then the reaction will proceed via SN2 mechanism. Whereas if the substrate is tertiary, then the mechanism followed will be SN1. So now what we have to look, before we proceed further, like what is the structure of the substrate? Is it a primary, secondary or a tertiary. So now we know primary basically will undergo mechanism SN2 mechanism, a tertiary will undergo SN1 mechanism, whereas secondary can react with either. It can either undergo SN1 mechanism or an SN2 mechanism, but the overall reaction is quite poor. So in this case, we'll be needing other factors which will influence the rate of the reaction or which will help us in deciding whether the reaction is SN1 or SN2. So from where do we start? What is the structure of the substrate? So in case of SN1 reaction, what we find is a tertiary alkyl halide will undergo reaction by SN1 mechanism. Why is this so? Because what we find here is that in a tertiary case, we get a tertiary carbocation which is stable. Secondly, because of the steric hindrance, the nucleophile cannot attack from the rear side. So in this case, the stability of the carbocation is the decisive factor. Whereas if we look into primary alkyl halide, and here both the nucleophile and the substrate take part in the reaction, so steric hindrance should not be there or it should be negligible. So what we find, either a methyl group which is methyl halide or a primary halide will undergo this reaction. Secondly, in this case, the carbocation formed will also not be stable. So now what we look into this is that we have to look into the stability of the carbocations which are being formed. But in certain cases what we find is that we have a carbocation like this. In this case, the carbocation is not planar. So SN1 mechanism is not possible, whereas if we look into the backside attack, then that is also not possible. So that means this will neither undergo SN1 mechanism nor SN2 mechanism. So when we talk of an SN1 reaction, what we have to look into is that the carbocation that we are getting, that carbocation should be stable. If we talk of simple alkyl substrates, then more substituted the alkyl group is, more is the stability. This more stability is because of the fact that this is being stabilized because of hyperconjugation here. Here we have a planar structure. So when we have a planar structure, what we find is that there is in hyperconjugation between p electrons and the sigma electrons of the alpha hydrogen, and we have number of hyperconjugating structures which will stabilize this carbocation. Whereas if we look into a primary carbocation, then this carbocation is not stable because here hyperconjugation is not possible. Since this is not stable, therefore the reaction mechanism followed here would be SN2, whereas in case of a tertiary carbocation or a tertiary substrate, the mechanism would be SN1. So just by looking at the substrates, we can decide whether the mechanism will be SN1 or SN2. Not only will the alkyl groups stabilize the carbocation, what we find there are certain other groups, like if there is a C double bond C along with a carbon which is having a positive charge, that is if we have a allylic group, then that will also, that stabilizes a carbocation. And because of this stabilization of this carbocation, it will undergo SN1. For example, if we look into this, the structure of cyclohexene alcohol, then what we find here is that the carbocation formed here is allylic, and this allylic carbocation is resonance stabilized. Not only this, the allylic carbocation which we are getting here is symmetrical. So as you can see here, the attack of the nucleophile can take at two places which are equivalent. So in this case, what we get here is just one product, which is allyl bromide. But if we have another molecule which is but2-ene-1-ol, or we look into its isomer, which is but3-ene-2-ol, then this reaction is very ambiguous, because here we will get a mixture of products. Now what happens here is, whether we start with but2-ene-1-ol or we start with but3-ene-2-ol, the carbocation which we are getting here, the allylic carbocation that we are getting here, is equivalent. Since the carbocation that we are getting here is equivalent, then in that case, what happens is that the reaction site is at two positions which are unequal. One is primary and second is secondary. So what we find in here is, now the question arises, where will the Br come and attack? In this case, the reaction is affected or is influenced by steric hindrance. So what we find is that position in which the steric hindrance is less, that is 1-bromo-3-butene is more. We get this is as an 80%, whereas the other isomer is 20%. So here, because of the allylic carbocation, we are getting two positions. Second thing that we have to take into consideration here is that this substrate that we are started with is a primary. And we said that a primary substrate would undergo SN2 mechanism. But in spite of being primary, this allyl carbocation is stabilized by resonance. So the carbocation formed here is very stable, so the rate of reaction through SN1 mechanism would be faster, and the stabilized carbocation will decrease the energy of activation, and this reaction SN1 will be more feasible than SN2 mechanism. Similarly, what we find in the next example, that is, if I look into 2-methyl-but3-ene-2-ol, then in this case, regioselectivity is a bliss, because in this case, again, the resonance stabilized carbocation is having two structures, because one at the tertiary carbon and one at the primary carbon. Now we know that steric effect is playing a very important role here. So what we get here is exclusively prenyl bromide, that is 1-bromo-3-methyl-but2-ene is the major product in this reaction, because here the steric hindrance is less and we are getting only this product. So in this case, regioselectivity is a blessing in disguise. Normally we say it is little difficult if we have a allyl compound and it is giving us two unequivalent positions, then we get mixture of products. Not only this, what we find is that even benzyl cations, which are again a primary cations, they will also undergo SN1 mechanism. And here there is no ambiguity as to where the reaction will take place. Reaction will take place only at the benzylic carbon, although the positive charge is there delocalized over the benzene ring also. But as we had discussed in our earlier lectures, that if the reaction takes place in either of the positive charges on the benzene ring, then the molecule will lose its aromaticity. So in this case, the substitution will take place only at the benzylic carbon and not over the ring. So what we've discussed till now is that is an alkyl group, and if we have a double bond in conjugation with the carbon which is having a positive charge, that is a allylic group or benzylic group, they will stabilize the carbocation and reaction will proceed via SN1 in spite of these carbocations being primary, because the carbocation formed here are stabilized by resonance effect. Second thing that we have to keep in mind is, again I have an example of a primary substrate here, that is chloromethyl-methyl ether. It is a primary. Now the question arises, will it undergo SN1 or an SN2 mechanism? In this case, again we will follow SN1 mechanism, because in this case the lone pair of electrons on the oxygen will stabilize the carbocation and it will help in the cleavage of the CCl bond. That is, it helps in the cleavage of this bond. So, and the carbocation that we formed will be resonance stabilized. So, we have an oxonium ion structure, or we can have a carbocation structure. So, if we have a carbocation here, then the alcoholic molecule will react at this site, and what we get here is a substituted ether, that is, we get a methoxymethyl ether. But in this reaction, again what we've seen is that if the group attached at the alpha carbon has lone pair of electrons, then it also stabilizes the carbocation through resonance, thereby increasing the chances of SN1 mechanism. Now a very, very important reaction which we will just touch here in brief, and then we will take it in detail when we talk of aldehydes and ketones, is the hydrolysis of acetals. This reaction also follows SN1 reaction. But by mistake, you can come to an idea. You may say, no, this is an example of SN2 mechanism. But the question arises that one at a single carbon, two electronegative groups are attached. Then what we find is that is the group which is more electronegative or which is more basic, which is less basic, that will depart. So in this case, what I've shown here is that if we have halogens, they will leave easily, or if you have OH2 group, that will leave easily as compared to a OH group. So when we go back to this slide in which we are discussing the hydrolysis of acetyl, then what we find is that when first the hydrolysis of the methoxy group takes place and this group leaves, and what we get here is an oxonium ion which is resonance stabilized. Now at this oxonium ion, there is interaction between between the pi bond and the positive charge, and this carbon becomes electron deficient where the water will attack. And then this water loses a proton and is converted into hemiacetal. So please do not make the mistake of commenting that this is a SN2 mechanism in which the bond cleavage and bond formation is taking place simultaneously. This cannot happen because the site, as you can see in SN2 reaction, is highly hindered. So the backside approach of the nucleophile is not possible at this site. Secondly, the carbocation which we are getting in SN1 reaction is resonance stabilized. So both the features, that is the stabilization of the intermediate anion formed and the steric hindrance, will push the reaction mechanism towards SN1 and not towards SN2 mechanism. Now I would like to quickly, in this reaction slide, again what I have shown, the which two groups between the electronegative groups X and Y, which will be a better leaving group. So we find which is the more, which is a less basic group will leave better. Now next point is, in this slide what I have done is, I have simply summarized what are the good substrates with which we can work in SN1 reactions. So tertiary groups which are stabilized by a allylic group or a benzylic group, species in which the carbocation is stabilized by lone pair of electrons on the adjacent carbon atoms. All these groups will undergo reaction by SN1 mechanism. Now, if we go on to SN2 mechanism, then in that case, what we know is that either a methyl group or a primary alkyl group is very, very favorable towards SN2 mechanisms, because these groups do not form stable carbocations, and secondly, in this case, the backside approach of the nucleophile is easy. But the question arises, are these the only two substrates? That is the alkyl methyl group and a primary alkyl group which will be able to undergo SN2 mechanism? No, there are some other groups also which will also which will help in SN2 mechanism. For example, allylic and benzylic groups which were facilitating SN1 mechanism also will facilitate SN2 mechanism. Because what we know is, in both SN1 mechanism as well as SN2 mechanism, the leaving group is important. So in this case, what happens in the previous case in SN1 mechanism, the question was the stability of the carbocation, whereas in this case, the question arises the stability of the transition state. So when we look into the transition state, what we find is that the electrophilic carbon is attached to two electron withdrawing groups. So these two electron withdrawing groups are decreasing the electron density at this carbon. So anything that will stabilize this transition state will help in SN2 mechanism. So what we find here is that the double bond will be delocalized, and since it is delocalized, it is decreasing the positive charge at the carbon, electrophilic carbon, and we get a transition state which is stable. The energy of activation will be less and the reaction will be feasible. Now we look into a substrate where there are two groups, electron withdrawing groups on adjacent carbon atoms. That is what we find here is that in this case there is a carbonyl group which is present at the alpha position to a carbon which is holding the bromine. So what we find in this case is that this carbonyl group will help in cleavage of the CBr bond, and it also increasing the leaving ability of Br. Now both these carbons, the carbon to which the Br is attached and the carbonyl carbon, are highly electrophilic, because what happens, Br pulls the electrons, at the same time carbonyl carbon is also pulling the electrons from the carbon to which the bromine is attached. So that means now the nucleophile can attack at either of these positions. But if the reaction takes place at C double bond O, at the carbonyl carbon, then this reaction is reversible. So what happens is that the reaction takes preferably at the carbon which is attached to Br, resulting in nucleophilic substitution reaction, and what we get here is a nucleophilic substituted product and not addition across the carbonyl group. Now if we go into closer look into the effects of the groups which are attached to the substrate, then what we find is that if there is a benzylic substrate and it is attached to a group which is electron donating, and if that electron donating group is positioned in a favorable position, that is, it can donate the electrons to the benzylic carbocation that is being formed, then in that case the mechanism will be SN1. Whereas if we look into the second example where we have a nitro group, This nitro group is electron withdrawing group. Since it is an electron withdrawing group, it will withdraw the electrons from the carbon, thereby destabilizing the carbocation formed. And this reaction, in spite of benzylic ion being formed as an intermediate in this reaction, it will not undergo SN1 mechanism because the carbocation intermediate is not stable. So what we find that just by modifying the substrate, we can switch over the mechanism. So what happens? Instead of SN1 mechanism here, the mechanism switches to SN2. So there is a very delicate thread between the SN1 mechanism and the SN2 mechanism. So one has to be very, very careful when we are looking at the substrate as to whether the substrate will undergo SN1 mechanism or SN2 mechanism. Because here what we've seen is that just by two groups, an electron donating group which is stabilizing a benzylic cation is favoring SN1, whereas a group which is destabilizing a carbocation will not favor SN1. The mechanism will quickly change from SN1 to SN2. Secondly, what we find is that if there is a carbonyl group also attached adjacent to a carbocation, that will also destabilize the intermediate because of minus I effect. So what we've done in this slide now is I've summarized which substrates are favorable for SN1 mechanism and which are favorable for SN2 mechanism. So just by keeping this in view, this slide in view, this chart in view, what you can do is you can quickly, just by looking at the substrate when you have a reaction that you have to proceed with, and you can compare which substrate it is tallying to, whether the carbocation intermediate formed will be stable in spite of being primary, or there is steric hindrance and the substrate will undergo SN2 mechanism. Now the second point that we have to keep into consideration is there is another very important factor, that is solvent factor, which can just tip over the reaction. That is, we know that in SN1 mechanism, the intermediate formed is a carbocation. That is, the intermediates involved are ions. So in this case, protic polar solvents will favor this reaction. In fact, most of the SN1 reactions are brought about by polar solvents, and we call these reactions as solvolysis reactions. What happens here is that the solvent molecule stabilizes both the carbocation as well as the nucleophile. So since the carbocation here is stable because of the solvation effect, and this is the intermediate which is formed in the transition state, so the energy of activation becomes less and this reaction proceeds quite easily. So what we say is protic polar solvents favor SN1 mechanism. For example, if we look into this slide, then if we compare the relative reactivity in solvent molecule, which is ethanol or water, then we find that if we take pure water, then the rate of reaction is 100,000 times faster than if we take pure ethanol. So what is preferable here is that we take water, it will result in a substitution reaction which will be favored by SN1 mechanism, because here the molecule is being stabilized by intermolecular hydrogen bonding. But now if we switch over the solvent to a aprotic solvent, in SN2 reactions also we need a protic solvent. Now what are two types? We face with two types of solvents. One is a polar solvent which has a high dipole moment, such as water, THF, alcohol, that is THF is tetrahydrofurane, or we have non-polar solvents like hexane and benzene. Nucleophilic substitution reactions, that is, those are bimolecular, they are also favored by polar solvents. But in this case, what we need is a aprotic polar solvent. Why do we need a aprotic polar solvent here is because if you remember, in SN2 reaction, the nucleophile is also taking part in the reaction. So here the strength and the concentration of nucleophile is also very important. And if we will take a protic solvent, that will solvate both the nucleophile as well as the substrate. So if it solvates the nucleophile, then the nucleophilicity of the nucleophile will decrease. So what we need is a aprotic polar solvent. So now if we look into a aprotic polar solvent, what this aprotic polar solvent does, it just solvates the cations, leaving behind naked anions. Now these naked anions will act as nucleophiles and they will help in SN2 mechanism. So what we find is that the protic solvents will favor these reactions, but a very small difference, protic solvent will favor SN1 mechanism, whereas aprotic solvent, which will only solvate the cation, leaving behind the naked anion, will facilitate in SN2 mechanism. So we can easily switch over from SN1 to SN2 just by changing the solvent. And then what we find here is that in SN2, when we went from a polar protic solvent to a polar aprotic solvent, then the energy of activation decreases in aprotic solvent and the reaction is SN2 is a favored reaction. The third point that we have to take into consideration, which is very, very important, is the leaving group. Now we know that leaving group is involved in the rate determining step in both the reactions, in SN1 reaction as well as in SN2 reaction. In SN1 reaction, the substrate cleaves to form a carbocation. So it is involved here. Whereas in SN2 reaction, we know that the reaction is taking place simultaneously, that is the attack of the nucleophile and the cleavage between the carbon and the leaving group. So here also leaving group is taking part in the rate determining step. So what should be the nature of the leaving group? Leaving group should be stable enough, should have so much of staying power that the substrate is stable. But at the same time, it should have just right level of reactivity to leave. So that it should leave easily, that is, it should not be a strong base, it should not be a strong nucleophile, it should be replaced by a stronger nucleophile, and it will help in the reaction. So now what we see in next is, what are the good leaving groups? Halogens are good leaving groups, followed by sulfide, then bromide, chloride, and a carboxylate ion. These are good leaving groups because these are weak bases of strong acids, conjugate acids. So what we find from this table is that triplet ion is the best leaving group, whereas if we look into this as compared to an acetate ion, because triplet ion is a weak base of a strong acid. Next point that one has to take into consideration is, along with the leaving groups, that means a leaving group should be that which is a weak base or which forms a stable base after leaving. Not only this, the rate of reaction is also determined by the nucleophile. So just by looking at the nucleophile, we can say whether the reaction will be SN1 mechanism or SN2 mechanism. Now the point to be taken into consideration is that the nucleophile does not take part in the rate determining step of the SN1 reaction. So SN1 reaction is not affected by the nature of the nucleophile. It is the SN2 reaction which is affected both by the concentration and the strength of the nucleophile, because there in rate determining step both are taking part, that is the substrate as well as the nucleophile. The next thing that you will take into consideration is what will be a good nucleophile, or how will you decide whether this nucleophile will favor a SN1 reaction or a SN2 reaction. Please remember, simple solvent molecules like water, alcohol, they will favor SN1 mechanism, whereas if we go into an anion, that is a negatively charged nucleophile, that is better nucleophile in case of an SN2 mechanism, whereas an uncharged conjugated acid is a better nucleophile for SN1 mechanism, and then strong bases will also favor SN2 mechanism. So what we look here is that if we have a negatively charged ion, that is a better nucleophile for SN2 mechanism. Then what we find, if we go down the group, then the atom which is larger in size, which is less electronegative, is more polarizable, and therefore it is a better nucleophile as compared to the atom which is coming on the top of the group. So that means iodide is a better nucleophile as compared to fluoride ion. So here in this table, again what I have done is place the strength, decreasing strength of the nucleophiles for you. That is, if we have a Cn minus, that is a very good nucleophile, followed by good nucleophiles like OH, and then we have reasonably good nucleophiles like water and methanol. So what we can say from here is that if we have water and methanol, that will favor SN1 reaction, whereas if we look at the top of this table like cyanide or SH or I minus iodide, these nucleophiles will favor SN2 mechanism. So just by looking at the nucleophiles, you can decide whether the reaction will proceed in SN1 or through SN2 mechanism. So what we've discussed till now is, that is the nature of the substrate, looking at the substrate, looking at the leaving group, looking at the solvent and the nucleophile. They will help us in deciding whether the mechanism will be SN1 mechanism or an SN2. Second thing that you have to keep in mind is, in case of vinylic, allylic and benzylic substrate, there is very little difference between SN1 mechanism and SN2 mechanism. So there we say the groups which will stabilize the carbocation intermediate will favor the SN1 mechanism, whereas groups which will stabilize the transition state, they will favor SN2 mechanism. Then again, a very small delicate line is the line between the solvents. That is, if we take a polar aprotic solvent, then SN2 mechanism will be followed with the same substrate, whereas if we take a polar protic solvent, then reaction will switch towards SN1 mechanism. Solvent molecules like water and methanol will favor SN1 mechanism, whereas strong nucleophiles will favor SN2 mechanism. And the leaving group is again very important in the reaction. So we see that a leaving group which becomes a stable base after leaving is a very good leaving group. Now I would like to concentrate more into nucleophiles. We will look more closely into nucleophiles. Normally we have a nucleophile, supposing I am doing the reaction of an alkyl halide with an alcohol, that is with aqueous KOH, alcohol will be a product. In this case, this OH can act as a nucleophile only through lone pair of electrons on oxygen, whereas there are other types of nucleophiles also which we call as ambident nucleophiles. What is an ambident nucleophile? An ambident nucleophile is a nucleophile which can act as a nucleophile through two states. At the same time, we also have ambident substrates. What is an ambident substrate? If we look into the substrate that is coming on the screen, then what we find that the resonating structure has negative charge at two places, one at the carbon and second at the oxygen. So that means in this case, the nucleophile can attack at the carbon as well as at the oxygen. So the two sites are available for bond formation with nucleophile. These substrates are known as ambident substrates. Similarly, we have ambident nucleophiles also. Here we will take example of cyanide and nitro. So what we find here is in case of cyanide, it can act as a nucleophile through two atoms. In one case, we have a negative charge on carbon, so it can act as a nucleophile through carbon. Whereas in the second case, it has a negative charge on nitrogen. So there it can act as a nucleophile through nitrogen. If we look into nitrite, here also we have two structures. It can either act as a nucleophile through negative charge on oxygen, or it can act as a nucleophile through lone pair of electrons on nitrogen. Now the question arises, how will it affect these nucleophiles, affect SN1 and SN2 reactions? So what we find is that when we talk of these nucleophiles, we have two sites here. If you look into nitrite, then in nitrite, oxygen is the more electronegative atom as compared to nitrogen, whereas in case of cyanide, nitrogen is the more electronegative atom as compared to carbon. So how do these electrophiles affect SN1 and SN2 reactions? So what we find in case of nitrite, it will undergo SN1 reaction and attack a tertiary alkyl halide through its oxygen, whereas cyanide will attack through nitrogen. And if we look into SN2 reactions, then in that case, the attack will be through less electronegative atom, and in this case, nitrite will attack or react with primary alkyl halides through its nitrogen, and cyanide will form a bond through carbon. So what we find here in next case is that is if we do the reaction with silver salts, then silver salts generally help in SN1 reaction by effectively generating the carbocation. So what we find, if we have a tertiary alkyl halide and we are doing the reaction with nitrite, then in that case we will get alkyl nitrite, whereas if the reagent or the substrate is following an SN2 mechanism, then in that case we will get a nitroalkane. Similarly, what we find in alkyl halide with cyanide, that if it is a benzylic substrate or a secondary substrate, then in that case the reaction mechanism would be SN2 and we will get a cyanide. Tertiary alkyl halides do not undergo substitution here. They will undergo elimination in this case, whereas if we do the reaction with the primary or a secondary alkyl halide, which is stabilized by other groups, then in that case we will get isocyanides. So in these reactions, again what I have shown you is that if you do the reaction with alcoholic KCN and the mechanism is SN2, then in that case we will get propane nitrile. Similarly, with a secondary halide, that is isopropyl bromide also, it will also undergo SN2 mechanism and we will get nitrile. Whereas when we do the reaction with AgCN, then the mechanism will be SN1 and we will get isocyanide. We have to remember that in AgCN, the nucleophilic site will be lone pair of electrons on nitrogen, whereas with KCN, the nucleophilic site will be the carbon atom. So I'll just repeat, in case of AgCN, it is the nucleophilic site and not the electrophilic site. The nucleophilic site will be the lone pair of electrons on nitrogen. So similarly, if we look into reaction with sodium nitrite. Then what we find here is that the mechanism will be SN2. It will follow a SN2 mechanism, and we know that here the reaction will proceed through less electronegative nitrogen, and what we'll get here is a nitro product. Whereas when we do the reaction with AgNO2, and if the mechanism is following is SN1, then in that case the reaction will take place through oxygen and we will get up in ending nitrites. So this is how ambident nucleophiles can give us two set of products. That is, if the reaction is following SN1 mechanism, then isocyanide will be the major product, whereas if it is following SN2 mechanism, then nitrile will be the major product. Similarly with nitrites, what we find is if the mechanism is SN1, then nitrite will be the major product, and if the mechanism is SN2, then the nitro compound will be the product. Now I would like to switch to nucleophilic substitution reactions in biological systems. Nucleophilic substitution reactions form a very important part in the biological systems. They seem to be very, very complicated reactions, but they are quite simple, and you will see how important they are. For example, we know that choline, which is a neurotransmitter, adrenaline, which regulates blood pressure, and nicotine, which is a nerve stimulant. These are three very important compounds which are operative in animals. Nucleophilic substitution reactions are not only involved in animals, they are also involved in plants. Choline, for example, is a neurotransmitter. It is not only important in animals, it is also important in plants. We've seen the phenomena of touch me not plant. If we touch it, leaves withdraw. That is, they shrink. It goes into itself. What is happening there? A choline, which is a neurotransmitter there, is transferring the impulse, and it is shrinking. Similarly, a neurotransmitter, which is a very important transmitter in our body, if it is not working all right, all our nervous system will go haywire. That is, there will be a short circuit and we do not know what will happen. So are very important, and these are synthesized with help of methionine in our body. How does methionine help? Methionine transfers methyl group from it to these receptors like choline, adrenaline, and nicotine. It helps in forming these receptors from the substrates in our body. How does this methionine work? Methionine works, it reacts with adenosine triphosphate, which is ATP in our body. In this, ATP acts as a substrate and methionine acts as a nucleophile through sulfur. And here, the phosphoric acid, the triphosphate group, is the leaving group because it is a conjugate base of a strong acid. So what we find here is that a nucleophilic substitution reaction is taking place and sulfur is attacking a CH2 group here, and it is replacing a phosphate group, resulting in a nucleotide, which is S-adenosyl methionine. Now this adenosyl methionine acts as a substrate in further biological synthesis or biosynthesis. So what we find here is that this is a simple nucleophilic substitution reaction in which methionine is acting as a nucleophile through lone pair of electrons on sulfur, and triphosphate group is acting as a leaving group. And what we get here is a nucleoside, which is S-adenosyl methionine. And now this methionine will act as a substrate in the further reaction. What we find is that two N,N-dimethylaminoethanol acts as a nucleophile. Here this molecule is acting as a nucleophile through lone pair of electrons on nitrogen and not through OH group, because N,N-dimethyl group is more nucleophilic as compared to OH. Now the second point is that where will it go and attack the substrate molecule, which is adenosyl methionine? It will go and attack at methyl group, because this methyl group is less sterically hindered, and it results in the formation of choline and the adenine molecule. So what we find here is that very beautifully in our biological systems also, nucleophilic substitution reactions are taking place. They seem to be very complicated, but what they are following is they are following either SN1 mechanism or SN2 mechanism and bringing about the transformations. In the next lecture, when we talk of the neighboring group effects, then we will talk of another very important biological reaction, that is the mustard gas. How it was mustard gas used in Second World War and how did it act as a toxin in our systems. That we'll be taking in the next lecture when we talk on the neighboring group effects. So what we've seen is that in biological systems also, nucleophilic substitution reactions are playing very important factor. Let us go into more detail, or let us go more closely into nucleophilic substitution reactions. And here I would like to take into consideration the neighboring group participation or the enchimeric assistance in nucleophilic substitution reactions. Sometimes what we find is that the rate of reaction is faster than can be explained by SN1 mechanism or SN2 mechanism, and even there is change in the stereochemistry of the reaction. That is, we are expecting either inversion will take place or racemization will take place, but neither of the two take place. What happens is there is retention in configuration. So how do we explain for this phenomena, for this unique property, or we can say for this abnormal behavior? So this is explained on the basis of neighboring group participation, which is also called as enchimeric assistance. What happens here is a substituent which is present on the carbon next to the group carbon from which the leaving group is going to depart. That group participates in the reaction, thereby increasing the rate of reaction and also changing the stereochemistry of the reaction. This is known as, if I define it, so that means I can define neighboring group participation as that group that will affect the course or the rate of reaction by changing its mechanism or by participating in the reaction. So what we observe here is the neighboring group participation, if I define it according to IUPAC system, is an interaction of a reaction center with a lone pair of electrons in an atom or the electrons present in a sigma or a pi bond. That is any group which is next to the carbon from where the departing group is going to attach. If it has lone pair of electrons, or there can be an interaction between the sigma or the pi bond, it will participate in the reaction and thus increase the rate of the reaction, and it will also change the stereochemistry of the reaction. So what happens in this case is, what we find here is, if we look into the mechanism briefly and quickly, what we find is that this G group, that is the participating group, here acts as a nucleophile and it attacks the carbon from the rear carbon. So what we'll do is, since we are running short of time, we will discuss this mechanism in detail in our next lecture. Hope this lecture has been useful to you.
With this note, thank you, ma'am. Thank you once again for giving your precious time as well as precious input to this very lecture. As Dr. Aparajita Chauhan herself said that we would be continuing further, we would be discussing more on the reactions. Till then, friends, if you have any queries or if you want to give your feedback regarding this particular lecture, then you can mail us at info.cc@nic.in. And for accessing this lecture, you have YouTube with you. With the help of it, you can access this lecture as we upload lectures for you, so that it becomes convenient for you to see these lectures, study these lectures ample of time. Thank you, ma'am. Thank you once again.
Thank you so much.